and I'm a CTO of KPIT Technologies. KPIT is the world's largest independent software company serving the automotive industry as a software integration partner for the last 20 years. Some of our solutions include real-time operating systems and middleware platforms which enable speedy software application development for our customers. Coming to the subject of cars. A modern-day car is one of the most complex devices for electronics as well as software. Not many people know that the complexity is more than a modern-day aircraft. Just to give you some numbers, in a modern-day car, there could be anywhere between 80 to 100 electronic control units, which essentially have one or more microcontrollers/application processors. And these are connected across 8 to 10 different networks, eventually connected to each other through a central gateway computer, using different technologies, networking technologies like CAN, LIN, MOST, FlexRay, and recently now also Ethernet. And all of this to top the challenge up is sharing data at real time, because control loops have to get executed, safety has to be managed inside the system. In the past, maybe about 15 years back, the lines of code inside the car maybe was about close to 2 million, which has increased to about 100 million lines of code recently, and is expected to go very soon to 300 million lines of code. So you can actually imagine the complexity and the scale of the software that goes inside the vehicle. Definitely it's an engineering marvel, optimizing many parameters like cost, performance, reliability, safety, facing stiff competition, and of course pressures on timelines. Car programs can take anywhere between 24 to 26 months for a new model launch. And sometimes the technology exploration in a new technology can go for a couple of years before a program launch activity is taken up. I'm going to talk today about 3 major trends that are currently driving the technology in an automotive, and I think most of you are aware of that. The first trend is electric powertrain, the second is autonomous driving, and the third is digital cockpit. Coming to electric powertrain, I think electric powertrain has been in discussion for quite some time. Its viability, its feasibility has been discussed quite a lot. But what has been interesting is recently in a concluded conference in Europe, there was data shared which shows that the adoption of an electric vehicle in Europe has actually surpassed their projections that they had in terms of the adoption. And hence, there is a urgency in terms of actually looking at what this technology means and how this technology could be successfully delivered by car makers to the market. Another interesting data that I saw is if you compare the adoption of a car over its previous mode of transport, which was horse carriage, and if you compare the transition from a horse carriage to the car, and with the current transition from a fossil fuel car to an electric car, the electric car is getting adopted at a much faster rate than the transition happened from the horse carriage to the car. It's interesting to see that electric car is actually adopting itself more faster than the actual car replaced the horse carriage. I think from a technology perspective, the real challenge is the battery technology, and maybe to get into a little bit of details into that, most of the batteries are either one or other chemistry of the lithium ion as a basic technology. What happens is these are all batteries with liquid electrolytes, and in liquid electrolytes, there is a problem of formation of certain crystallization structures called dendrites, which can actually short the battery and render it useless. So you have to have a lot of control in terms of how you charge and discharge these batteries, and this also puts some limitations in the mechanisms of trying to charge these batteries. So while charging, if you charge it too fast, there is a chance of these dendrites getting formed. So you have to charge it pretty slowly. Now, if you look at what happens as a result, a normal modern-day lithium-ion battery has to be charged at a home charger, which is at a lower power. It takes about 7 to 8 hours to fully charge the battery. But let's say in a supercharger situation where the power of the supercharger is much higher than what you can deliver at home, it can be done in, let's say, 1.5 hour time frame. This 1 hour is a very magic number for a battery. If you charge a full battery in 1 hour, that charging current is called, in terms of terminology, a 1C current. Whatever is the current required to charge the battery in 1 hour is actually called a 1C. Now, if you typically charge a lithium battery in a 1C mode, it will actually impact the life. So you have to charge it at much lower rate, current rate, which means it has to be charged at 0.4, 0.5 C, especially as it starts getting closer to 90% plus charging capacity. Okay, so you are limited by how you charge the battery in terms of the time. So what happens as a result, because you take a lot of time to charge the battery, you end up actually providing a larger battery so that the anxiety of the customer to travel has to be dealt with. So to compensate for the charging time, which is more, you actually put a battery at 500 kilometers, 600 kilometers to throw the anxiety out, which means that the battery size significantly increases, and battery today is the most expensive component inside the car. And as a result, what happens is the overall cost of the car shoots up significantly. Now there is a disruption coming along this line now. So there is a technology called solid state battery, where the battery electrolyte is not a liquid, but mostly ceramic. And some of the production challenges of the ceramic and brittleness when it will be solved, this faster than the current lithium ion, which means you could actually take a car to a charging station, a supercharger, and maybe charge it in 8 to 10 minutes to its at least 95% capacity, which is phenomenal, because that means that the anxiety will actually go down of charging it, which can allow us to reduce the size of the battery and as a result reduce the cost of the vehicle significantly. Now, this one specific thing is going to be a significant disruption, and while the problems of the manufacturing of the technology is getting solved, looks like this is going to accelerate the adoption of the electric vehicles in almost all the regions of the world. There are many companies doing this research, working with partners to make this happen. This will be a reality very soon. The second trend that I'll be talking about is the autonomous vehicle, which is again a very popular trend. Various companies are at various stages of making the autonomous vehicle happen. I won't go into the technicalities of how an autonomous car is specified in terms of what it can do. There is a SAE grading from L1 to L5. Let's look at more in terms of what it means. So today, most of the technology is come to a state of art where you can actually handle various scenarios of driving the vehicle autonomously. This obviously gets more and more difficult as you get into higher disorganized traffic scenarios, especially on the city road, where anticipating some of the things becomes a challenge. But for most of the other controlled areas, you'll see more and more launches happening, especially, for example, in the commercial vehicle implementation. There's a lot of value to bringing an autopilot on the highway, where there is expectation that trucks will on certain highways travel without drivers. The trailers would be actually taken to a point on a highway where it will be connected to a pod that can actually drive across the highway without any driver, and then it could stop at one place where the trailer could be taken off and added to a truck that actually has a driver and taken for its last mile delivery. So this seems like a very technically feasible and business-wise viable solution that will be experimented, and you may see it coming mainstream very, very soon. Autonomous has shown open research and technology development. For example, for a full autonomous system to come into picture, most of the technologies today use laser-based sensors. Now, laser is extremely costly, and hence viability of using them from a cost perspective is a challenge. So the laser technology is going through a change in its basic technology, where instead of moving lasers, you would have MEMS with the micro mirrors deflecting the laser beam. So instead of a mechanical movement, a very micro movement happening inside a chip that will allow the laser to work. These are called digital LiDARs. You would also have some of the radars getting into much higher resolution where they will overlap into the space that a LiDAR as a sensor is using. So there is a lot of technology related research happening, which again becomes mainstream in next couple of years, which should allow the cost of an autonomous vehicle to reduce significantly. Autonomous is on one side there is a technology visibility issue with all the complexities that exist. On other side there is a cost issue, which I spoke about in terms of new technology reducing the cost. And third, there is also a social regulatory issue in terms of what happens if an accident takes place. And there is work happening on all these three areas. I will speak more about this slightly later in this session. Let me take the third trend area, is the digital cockpit. A huge amount of innovation is going to go into how to appeal the car aesthetically from inside the car. How do you increase the experience, the consumer experience inside the car, or enhance the consumer experience inside the car? And you'll see multiple displays being used instead of the current mechanical gauges. These will be high-end display devices that we are used to seeing in our phones now. And of course, there will be advancements in these displays. So some of these displays could actually be heads-up displays. These displays will project on the screen. You are already having vehicles that do heads-up displays, but you'll see more and more enhancements and refinement into this particular technology. And then, of course, there will be tactile displays. There is a merit for a person who's driving the car for him to feel the display. And of course, voice as a method of interfacing with the vehicle is becoming very, very popular. Alexa, Siri, all these technologies will basically make inroads into the car at a commercial scale to make your interface with the vehicle through voice much more easier, simple, and absolutely more convenient to make things happen. And of course, there is going to be rear seat entertainment for family cars. Your subscription of all the Netflix or Amazon Prime being available in the car, enabled through 5G technologies, so you can actually stream data, stream videos, so you don't have to get into creating content, saving the content in the vehicle. All this is happening at the moment. Proof of concepts are running, advanced research projects are running, and technology is coming together to make this happen for you in the next 5 to 10 years time frame. So now, if you search for internet for all that I've spoken, you'll find a lot of material on it. This being an engineering school discussion. If you take, for example, the technology of autonomous, right? And if you take a look at what goes inside the autonomous is, of course, neural networks that are being used for perception of objects. Sensory devices like radars, LiDARs, cameras are basically sensing the environment. You are converting this environment information into some kind of perception. And of course, these perceptions are done through neural network. Now what neural networks, while the vehicle is actually performing its work, it is also learning as a result of that, right? So there are situations where the vehicle is running, it is doing its work, but it is also knowing what the driver is doing in particular scenario. So it is able to sort of bring a certain amount of data, not just on what the vehicle perceived or what the vehicle saw, but also how the driver acted in certain cases. And if you look at this data is extremely important from a learning perspective. So if a single car encounters a specific scenario, a corner scenario in a specific place, in a specific city, in a specific country, all cars have to get benefited out of this scenario. So what happens is this car is going to share its learning through some kind of an infrastructure, cloud infrastructure, which will get processed and then get ready for all the other cars to be deployed. And as you can appreciate, because this is related to learning very fast, and if you make it available to other cars, of course it will increase the experience of all the other car drivers. This has to be a fairly frequent process. The requirement for neural networks to learn is actually pushing the requirement for a continuous update of the vehicle neural network models. And as a result, connectivity is becoming more important. So faster connectivity, high bandwidth connectivity to the car is important. And once you have that, the effectiveness of actually updating this is demanding some kind of a central computer that basically deals with all of these. So a central compute architecture, which is actually in contrast to the current vehicle architectures that are largely distributed. So as I started in my introduction, a car is having anywhere around 100 different controllers controlling the vehicle. And the reason why this architecture existed is because how the car industry actually worked in the past, where it sourced the functionality from various suppliers, one giving brakes, one giving engine, one giving, let's say, Windows system for the windows to come up and down. And then the car maker actually integrated things. Now, if you look at the needs of the autonomous driving vehicle and the fact that they need to be updated very fast, there is a demand to create a place which can get updated, or a computer that can get updated very frequently. And as a result, you are basically wanting to do everything on a central computer. And because essentially the networks that are spread across the vehicle, the 6 to 7 different networks or 10 networks that I talked about, are essentially not as high-speed networks as we are used to see in our broadband scenarios or the Netflix scenarios. These are actually networks that go up to 10 Mbps speed and not more than that, which is actually driving the need for what is called as a central architecture. And the moment you come onto the central architecture, you are essentially disrupting the mechanism, you are disrupting the current way things are done, because most of the software today was being written by a supplier, and the supplier used to supply this electronic system with software to a car maker, and then it is to be integrated. So now, since there is only one place where multiple suppliers have to collaborate, there is going to be a little bit of disruption in the way of working, and as a result, maybe different types of solutions to this disruption can emerge. So one solution is the OEM writing the software themselves. Second solution is suppliers have to collaborate with themselves to create a common solution. Third, new set of suppliers will come in because electronics will actually be sourced from only one supplier as a central compute architecture. So maybe there are more space getting created for software companies actually selling only software to car companies. So these kind of things are actually going to create disruption in the ecosystem. The second big change that happens as a result of this architecture is the concept that is very prevalent in the phones, that a phone, essentially a smartphone, is always it's a product in making, right? It's never complete. Minimum viable product. And through software updates and through application updates, its functionality, reliability, security keeps on getting enhanced. So I think this concept was absent in the car industry. Now it will become a new thing that will happen as a result of the changing architecture. So you'll see more and more upgradable features being downloaded into the car to make the car better and better from a user experience perspective. And of course, when you talk about software becoming upgradable and changeable with more frequency, you will start seeing also different kind of hardware getting inside the vehicle. So the chips will become more and more powerful. In a car, you're always, especially in an electric car, you're always going to optimize it for power versus performance ratio. So you need high performance at lowest power because power is to be saved.
Hey there. Subscribe to my channel. And also press this bell icon.